All right, we're getting into chapter 15 today. We are beginning chapter 15 with a discussion on something called the common ion effect, which will get us into our discussion on buffers and how it relates to acid-base solutions. And then the end of chapter 15 deals with some solubility calculations. And so let's go ahead and start off with the common ion effect. It's a pretty easy thing to understand and not actually too much different from your equilibrium calculations that you guys have done from chapter 14 with acids and bases. So let me give you a minute just to kind of jot that down. Actually, we'll cover this first. Okay, what we're dealing with here with the common ion effect is we're dealing with solutions that contain a weak acid and its salt. What I mean by that is, for example, let's say we've got a weak acid, hydrofluoric acid. Its salt would be something that has a fluoride ion as the anion. So an example of the salt for that would be sodium fluoride, NaF. So that's a weak acid. That is its salt. Basically, the salt contains the conjugate base of this weak acid. So if I look at these two things separately, hydrofluoric acid is a weak acid. It will partially dissociate into hydrogen ions and fluoride ions. And if I have in that same solution, so let's say I've got hydrofluoric acid, it's aqueous, all of these are aqueous, sorry, in solution, and then I throw some sodium fluoride in there. We're going to look at those separately here. Sodium fluoride is an ionic compound, so that means that it's going to completely dissociate into sodium ions and fluoride ions. What's going to happen here is when I take this sodium fluoride and I add it into a solution of hydrofluoric acid, what I'm doing is I'm adding fluoride ions. And so when I do that, it actually gets added to the product side of this reaction, or this dissociation of the weak acid, hydrofluoric acid. And when that happens, when I add more fluorine, or fluoride ions, I should say. When I add more fluoride ions, it's going to shift this equilibrium to the left, because it's just like any, the Le Chatelier's principle. When I add fluorine here, I'm adding something, I'm adding concentration of fluoride ions, so to get rid of that and to compensate for that, this reaction is going to happen in the reverse direction more to compensate for that and to get rid of the extra fluoride ions that are there. And because of that shift, not only is it going to reduce the amount of fluoride ions, it's also going to reduce the amount of hydrogen ions that are produced in that reaction. So let's go ahead and summarize that up here. Go ahead and copy this down. Okay, so this just summarizes basically what we talked about. Adding sodium fluoride to hydrofluoric acid solution adds fluoride ions to the product side, shifting equilibrium to the left. We get less hydrogen ions produced, so a smaller percentage of dissociation. Now, let's just address something right now, because it's a common mistake throughout this whole chapter. So, I don't know, make yourself a note, or common mistake. Students will see the wording of the problem say something like, we've got sodium fluoride added to a solution of hydrofluoric acid. And so they automatically think, okay, those two things are combining together, so they write this, HF plus NaF. That is wrong. Do not do that. No. Do not combine those together on the same side. A rule that you should remember is that partners must be on opposite sides. And when we say partners, I'm talking about the acid, hydrofluoric acid, and its conjugate base, which is that fluoride ion. They've got to be on opposite sides, and so that fluoride ion has to be added to the product side, which we kind of talked about over here as we looked at them separately. But if you see that, two things combining together, and you've got a weak acid, its conjugate base, that you do not put them together on the same side, you don't add them together, that fluoride ion is being added to the product side. And we'll see that more as we go through some of our calculations and buffer problems today. So let's go and do a little example of this. Okay, first of all, a quick reminder from chapter 14. This is just a period, so it should be separated there. You guys calculated the percent dissociation of 0.1 molar acetic acid. Okay, go ahead and take a couple minutes just as a review. Oh, by the way, acetic acid, you should know that formula is, I'm trying to think of where I want to do this, HC2H3O2. You should also know that a common way to write out the formula for acetic acid is CH3COOH. Same thing. If you count up the numbers of hydrogens, there's 2, there's 3, 4 hydrogens, 2 carbons. The reason why they would write it out this way is it's kind of a structural formula, so it kind of tells you how it's structured. So you've got a carbon with 3 hydrogens, so that's that part right there. And then that's bonded to another carbon, that's this part. That carbon is actually bonded to 2 oxygens, so I've got a double bond on an oxygen here, single bond on an oxygen, which is then bonded to another hydrogen. So writing it out separately like this tells you something about the structure of acetic acid. Just kind of a side note, something you should know. Okay, so calculate percent dissociation of 0.1 molar acetic acid. Okay, this is from chapter 14. I'll give you guys a couple minutes to do that. Oh, let me give you Ka just to make it easy for you. Ka of acetic acid, which if you weren't given that number in the problem, you could just look it up. So 1.8 times 10 to the negative 5. Okay, you should get as a percent dissociation 1.34%. And if you're unclear on how to do that from chapter 14, then you need to learn how to do that. But today we're kind of moving on, talking about the common ion effect.